Okay, welcome everybody. How I did my lerping was like this here. One little C++ trivia is if const_expr debug. So if const_expr is a compile time if statement. So you can have an if statement that runs in the compiler, essentially. So if you compile your code with debug set to true, then all of these lines that I have in my code that say if const_expr debug are included into the executable, and if debug is set to false, then it is not. And so basically I can turn on printing out all the things that are happening in my code, or I can not. And that's it's similar to an if statement, except if you have an if statement, it actually runs when your program is running. It'll constantly keep saying, "Is debug true? Is debug true? Is debug true?" And if const_expr, that line will never appear. That if statement will never appear in your output code, because the compiler will either, if debug is true, then this line of code will just appear there, and if debug is false, then this whole line will vanish from the source code. So we used to do this back in the day by doing something like this. If def debug I or whatever. Like that. So we would compile our code, compile with like g++-d debug main.cc. And if you compiled your code with debug defined, then this line of code would appear in your source code. And if you compiled it like this, then it would not appear in your source code. The preprocessor would excise it. It would cut it out of your source code. And so this is a very, very common approach. In fact, if you use like Visual Studio, there is debug mode and release mode. And it's very common to have two different, ways of compiling your code right out of the gate. There's debug mode and release mode. And you can do things like this and have different code run when you're in debug mode and when you're in release mode. Of course, there's always the risk that you break something. If you do something bad, like have an if statement here or something, if debug is on, then it'll print hi, and if debug is off, then this will be part of this if statement, which is really, really dangerous. So, do you guys understand if const_expr? It's basically the same thing as this, kind of. Little bit of new C++ knowledge for you early in the morning. Yes, you guys awake? Hello. Hazelton, have you seen this one before? Good, better than me. I was woken up 2 hours ago by a plumber. So. Okay. All right. So that's a little bit of new C++ knowledge, and this is also pretty important to know because a lot of people still code this way. Okay. This is a very common thing. -D, the -D flag, stands for define something for the preprocessor. So debug is defined for the preprocessor. It's the same thing as doing this. That's this line here, define debug, is the same thing as that. Okay. But for my code, up top some here, I just have a a variable. Okay. And if you make a const expr, that means it must be guaranteed a compile time determinable value. In the case, this is actually going to generate the same code, to be fair. But some people like writing const expr. Okay. So it is guaranteed compile time determinable. That's what const expr means. It means the compiler can determine everything we need to know about this. So it doesn't generate code. Been awake since 6 because your dog's eating when you sleep. Yeah, that's fair. Okay. That's my old API key, so that doesn't hurt me at all. All right. Yeah. Wow. I had a lot of includes in there. That's funny. Okay. So we're basically done with our graph theory topic. Markov is going to be our last graph theory. Depending on how well you do, I might even have another graph theory problem for you, because it's really important that you guys get that there's a core mechanic to graph traversal of like having a process list and a to process list, and you take something off, add all the kids to the to process list, add it to the process list. That pattern repeats over and over again in all these different graph theory applications. And how many graph theory applications are there? A lot. There's a lot of graph theory applications. Okay. So let's see how you guys did on the quiz, and then I'll know whether or not I can keep hammering you guys on this or have mercy. Not good. Okay, alright, so let's do this. What is shortest distance from 8 to 4? That'd be 7. Okay. So, yeah. Okay. There's one person that didn't get it. Okay. Use the same graph above. What is the total cost of a minimal spanning tree? So we can do this one in OneNote over here. If you're using mobile, yeah, I can see why you get that one wrong. And I have updated all of your points on the previous quiz by 1. So if you didn't take the quiz, I did. Yeah. Oh, what's going on here? If you didn't take it, then I didn't bump up your points. Okay, so let's do crystals. Okay, so what is the lowest edge weight anywhere within the tree? Where is the lowest edge weight? Do crystals out of 1. Okay, and then we'll do this one. Now which one? Still says 1 out of 2 for you on the quiz. I don't know. I could have screwed up your points or something. Okay. 2. All right. So we'll add a 2. We'll add a 2. So you see, for crystals, we're growing a forest. We've got 2 different trees going on here. Okay. And you don't add an edge if it's going to, like, let's say that there was a route here that costs 3. You don't add this one to the minimal spanning tree because it's going to add 2 nodes that are already within the same set. So what you do is you have a data structure, you have multiple sets, essentially. And in the STL, you just use the set class, and you just have multiple sets. You have a vector of sets. And then you can merge the sets together. I think there's even a standard library function for that. C++ set merge. set of chars, and then it merges the two of them together. Yeah. So what you do if you ever connect these things, you merge the two sets together. Okay. Then delete the other one, which might not be necessary. Anyway, so the point is like if you were looking at an edge and you wanted to see, should I add it? If the two nodes are already within the same set, which you can do with contains, right? Then you don't. That's how you stop yourself from getting loops and things like that. Okay. That's the only little tricky bit there. All right, who should we add next? Which edge gets added next using crystals? Yeah. It's very easy for you guys. 1, 2, 3. All right, now who do we add? 4. All right. And there's a 4 over here. And so these two guys just got merged together, and then who do we add now? 8. Now, not the 6, right? Because these two are already part of the same set. Right? That's why I picked this graph. So these two are already part of the same set, so we don't add this one. We don't add this one, we add this one. And then we just add up all the weights here. 5, 6, 7, 10, 16, 17, 25. Yep. So half of you got the minimal spanning tree, right? So better, we'll still do more. And then max flow. Ooh, that is not good. All right. So the max flow from 0 to 2. All right. So what is the max flow from 0 to 2? Okay, so what is the shortest path from 0 to 2? 8. Mm-hmm. Okay, so let's look at that shortest path, and then what is the max flow along that line between 0 and 2? Yeah, it's the minimal of the link. Okay. So we're going to say, so we send 2 gallons a second this way. All right. Now this one is saturated. We can't use that anymore. This, for all intents and purposes, we can just delete this edge out of the graph. It's not going to come up in any of our future calculations. We just need to write down the flow that we've used. Okay, what is the shortest path now? 9. Mm-hmm. So what is the max flow along this line here? Also 2. Okay, so coming this way, 2 out of 2, 2 out of 2, 2 out of 3. Okay, so we've sent 4 gallons per second here. What is the shortest path now? And this is disconnected, right? Because this link is saturated. So what's the shortest path now? 13, right? So this way, and this way. It's actually not 13, by the way. It's, what's the shortest path? It's not 19 either. What's the shortest path? $17. Very good. Because this one has 4 left, right? So 13 plus 4 is 17. So what is the max flow along this line? One. Right? So every time you do max flow, you sort of mark down the capacity as you use it. Yeah, so this turns into 3 out of 6, right? And then if you want to ask yourself, you could be writing these things down as you go along, or check this out. This is our source. This is our sink. Look at the outgoing flow from the source or the incoming flow to the sink. We got a 3 and a 2. So 5, or the outgoing is 2 plus 2 plus 1, 5. So the max flow through this network is 5. Yeah, I'll give you the point, Brian. Give me a second. I know there's one student's grade that I screwed up on. I accidentally deleted their old grade. Let me just, it's probably you then. 10-7 quiz, I think. Okay. Okay, so we'll do more graph theory questions until the average kind of clamps up. Okay. And there's Evanton Karp and Ford Fulkerson. So you can think of it as, let's see, is this one? Let's see. Okay. So find a path, saturate it, 5 out of 5, 5 out of 7, 5 out of 8, and then find another one. You just keep doing that. Yeah, and so there's a little bit of a twist to it, but what I've told you will work. BFS for finding nonlinear paths. Yeah, so max flow and min cut. So basically, max flow is the same as min cut. If this is your network, the number of bridges between A and B in parallel, then you need 5 bombs to take out the connection between A and B. So the max flow algorithm and the min cut algorithm are the same thing. So, all right, and that's a cool website. It's neat. It's got implementations. I wonder what they have for Dijkstra's. Let's take a look at the Dijkstra's. That's Russian. Okay. Data structures. Let's see here. Graph theory. Graph theory. All right, cool. Yeah, cycle detection is another good one. It's very useful in parallel processing to detect like deadlock and things like that. Max flow, graph check, Boolean set of ability, Dijkstra's. Oh yeah, and somebody asked about shortest paths when you have negative weight. Yeah. So Dijkstra's. All right. Let's look at their implementation here. Dijkstra. So what is I really like it when people don't use single letters, because now we have to guess what S is, what D is, and what P is. You know? Create an array D, where for each vertex you store the current length. Okay, so D is the distance from the source node to that vector. Okay, so D is our solution, essentially. Initially, the distance to the source is 0, everything else is infinity. So if it's disconnected, it won't. It'll show an infinite distance. Okay. All right, then what is P? probably is what I'm guessing, but I don't see it on here. And then S, what is S? Size of the graph? Yeah, probably, because they're doing this in, maybe? Is it size? Source. No, that's the source node. Okay. So they have a vector of vectors of pairs. So a pair is just two numbers together. So they could have made a struct containing two integers. Instead, they just used a pair for that. It's part of the hashtag utility header. So that's the adjacency matrix. So the adjacency matrix is going to be, what is that? Probably weight or something like that. It's really annoying when people don't name their variables very usefully. So that is the size of the adjacency matrix. So the distance is set to infinity. The parent of okay, so the parent of everybody is set to -1. The distance to the source node is 0. Are you guys with me on like variable names like this? Like a lot of people write code this way, you know, but you have to, like, if they just had a comment saying like S is the source node, you know, it'd be a lot easier, like on me, so I don't have to scroll up and look at it. So here is their Dijkstra's implementation. So the distance to the source node is 0, and then they're going to do a for loop for n equals 0 as less than ni++. N is the number of nodes in the graph, so they're doing a for loop because at most you will add n cities or whatever, right? If there's n nodes on the graph, at most you will add n cities. Ooh, look at that bad implementation. I just like looking at documentation where it looks like they're trying to do security through obscurity. Yeah, but just documentation saying this is what the variable is, it's so nice, you know, because like single letters, like is that source? Is it sync? You know, like, you know, what, D, P? Like, there's a lot of words that start with D, a lot of words that start with P, you know, and so you have to kind of like, you know, scroll up and kind of decipher what they're trying to do. And then now we have a U and we got a V and stuff like that. Okay, so we're making a vector bools called U of size n. They're all set to false by default. So what is U? Let's find out. Okay, so for every city on the map, we start with v is equal to -1, and so for int j equals 0, j is less than nj++. If not, uj and v equals -1, or dj is less than dv. So this is finding the smallest total distance to a city that is not already on our processed list. So u is our processed list. So it is set to true. So you've got, if you've got 10 cities, you got 10 booleans all set to false. And they don't start with the starting one in the processed list. So the first time through the list, it's going to find dj is less than dv. That's out of bounds, isn't it? Is that out of bounds? V is -1. Oh, yeah, if V is -1. Okay. So if V is -1, then it sets V equal to J. So the smallest distance we found is going to be, yeah, the first time through the loop, it's going to be the first node. Okay. Or the first person that is attached to the graph that we haven't processed yet. So that's our process list. And then it's going to, basically it's going to loop across all of the cities that are attached to the cities we've already processed and find the one with the smallest total distance, translating that into English for you. Okay. All right, see it, Cheryl. Okay. If we cannot find anybody, then the smallest distance, is infinity. That means the graph is not connected. There's some cities that are on the graph but are not attached to our source, so we stop early at that point. We add the smallest total distance from start to our processed list, which they're doing with just a vector of booleans. And the reason why I said, ooh, this is a bad implementation, is look at the running time of this. What do you guys see for the running time? What big O is this? That's cool. This is the processed list. This is the to-do list, to-process list. Sometimes called the frontier, a tentative set. Yeah. It's different names for it. So this is a tile-based. This is actually pretty much the algorithm you had to do for bridges mountains. They're coloring it based on distance or something. Color representing the distance. Yeah. And then each tile has its parent location, so it just backtracks along the line there. Using a priority queue is a better way of doing it. Okay. So we rather than doing an order n search for the nearest graph, we do this using a priority queue. And so the priority queue will give us the shortest distance in log n time rather than n time. Okay. All right, so so they're not using a data structure here. They're just sweeping across the entire vector, including all the nodes they've already processed. All those will just keep getting read over and over again. So if you have 1,000,000 nodes in your graph and you're on the last 3, it's still going to read over all 1,000,000 nodes to try and find this one with the shortest total distance. Okay. Add it to our process list for every edge and the adjacency. So now they're using modern C++. Good for you. Okay. For every edge in the adjacency list, which is where? Here. And so it's going to get it's a vector of vector pairs. So edge here is going to be a vector of pairs. So it's going to return the entire basically adjacency list. Okay. Okay. So 2 equals edge dot first. Oh no, it's not a vector of pairs. It's returning all the pairs. Okay. So for our current row, I was going to say that was really bad. So for if we're currently processing node 5 just got added to the process list. This is adding all of the children to the to-do list. Okay, so it's grabbing all of the pairs, which is the connections from our current city to all the other cities. So a distance of 5 to Paris, a distance of 10 to Brussels, that kind of stuff. And because Dijkstra developed this algorithm when he was at a cafe in Belgium or something like that, or Amsterdam or the Netherlands somewhere. I don't know. Okay, so for every pair. So for basically every connection we have, 2 and the length. So that the first part of the pair, which of course is not documented, is the person we're connecting to, and the second part of the pair is the this is an adjacency list. It's not an adjacency matrix. Okay. And the second one is how far they are away. So we might have just 3 cities we're connected to: Brussels, distance of 5; Berlin, distance of 20. That kind of stuff. So the first thing is the city. The second one is the distance, and then we just check the adjacency. The distance list. This is the list of the best distance we've seen. If this new route has a lower distance than the one that's in there already, which by default is infinity, then the best distance we found is the new one. That's the heart of Dijkstra's right there, right? The distance to a new city is the distance to us plus the distance from us to them. That's Dijkstra's. Screw that up, you get a minimal spanning tree. If you add one more term, total distance from the end, you get A star. And then the parent of that city is us. And that's it. That's the whole algorithm right there. So, all right. I think the story was like, he was at one of those magic cafes or something. Rotterdam to Groningen. So there you go. What is the shortest way to travel from Rotterdam to Groningen? City to city. It's the algorithm for the shortest path, which I made in about 20 minutes. So if you're ever feeling smart, just remember Dijkstra not only came up with Dijkstra's algorithm in 20 minute, but he was in Amsterdam. Okay. And he just sketched it out on a napkin in 20 minutes. The location is still readable. In fact, it is in fact quite nice. One of the reasons why it is so nice is that I designed it without pencil and paper. You didn't even write it down. That's cool. One of the advantages of designing without pencil and paper is that you're almost forced to avoid all avoidable complexities. Eventually that algorithm became, to my great amazement, one of the cornerstones of my fame. Okay. So, there you go. Megaflex, yes. Okay. So if you're ever feeling smart, just remember Dijkstra developed Dijkstra's algorithm in 20 minutes in his head. And if you're ever feeling dumb or a phony, just remember Berkeley invited me to speak at their data science conference with me knowing absolutely nothing about data science. So it goes both ways. It goes both ways. Spoke in front of a large crowd of people virtually on data science, knowing nothing about it, at Berkeley. I still have a Berkeley Gmail account or something that it occasionally tries logging me in as against my will. Okay, so that's it for graph theory. I will continue hitting you with quizzes until I'm happy with your knowledge, and then I will put up a competency exam for it. Okay? And then we will start on recursion. We'll just take a break now because this seems like a good stopping point. If you have any more questions about graph theory, if you have questions about Markov, like you need to start cracking on that, that's due next week. But I would start on it soon because there's a lot of... The biggest way that the Markov assignment can go wrong is you just roll the dice wrong. Because you have to roll the dice exactly the same way that I roll the dice. And so the comments in the code explain exactly how I want you to... If you're currently at Glock, then the comments explain exactly how you roll the die and then go from my Glock like Voltron and how you sort of randomly move through the world like that. Okay? So I would start now though, because if you get to the last minute and it's not working right, you're going to fail the test cases. So just get cracking on that as soon as you can. Take a day off. I know a lot of you are up till 6 in the morning or something working on the Dijkstra's assignment. Okay, so we'll go ahead and pause here, and we'll come back at We'll come back at 11. We'll give you a 20-minute break. All right. So our next big topic is recursion. So we're going to completely shift gears here and go from programming heavy to math heavy. Okay, so you guys have all written recursive algorithms before, I'm sure. CSI 41 tree traversal is usually done using recursion. CSI 40, we write a function like the Fibonacci sequence and things like that. Has anyone here not written a recursive function before? No, everyone knows. Okay. So, a recursive function is when a function calls itself. So in this case, we've got a function f, and it's going to print a hello world. We've got a constant expression here that's going to set a variable called limit to 100,000. I'm not streaming? No. No. Come on now. And tell me how many times it's going to print hello world. Take a moment. Look at the code. How many times is this code going to call itself? How many times is it going to call f and print hello world? A 100,000 times. That's a good guess. It's wrong, but it's a good guess. Zero times. No. Let's say that main calls f. Let's say that main calls f. How many times is it going to print hello world to the screen? It'll be at least one. So we've got 100,000, we got 0, we got infinite. I think we got our bases covered here. Why do you think it's infinite, Gregorian? McCohen, what do you think? Main calls f. It prints out hello world, which is at least one. Is 0 greater than 100,000? No, so it doesn't return. So then it calls itself. Prints out hello world. Is 0 greater than 100,000? Nope, calls f. Prints out hello world. Is 0 greater than 100,000? Nope, calls f. X does not change. Yeah, x is supposed to be changing. We can tell that x is supposed to be changing. X is not changing. So this is in fact an infinite loop. So what if we fix that? What if we add 1 to x? This is a global. This is going to track our global state, which isn't exactly a good way of doing this. But so the only change we made here was to make this incremented. How about now? How many times is it going to print out hello world? X is not being sent as an argument. That's true. X is a global. So every version of f is going to have access to the same x. We are presumably in a single-threaded code. We don't write globals like this in case you multi-thread, but in this case it's single-threaded, so it's okay, I guess. So how many times is this code going to run? How many, no, not run. How many times will it print hello world? What do you think? Main calls f, prints out hello world. It's going to be at least 1. How many times is it going to print hello world? What do you think? A 100,000 times. It's a good guess. We do have the number 100,000 in here. Is it 100,000 though? How can you tell? Corrente? What do you think? X is the same value? Nope, it's a global. So every time we increment X, this global variable here changes. So X is going to be 1 the first time through the loop. It's going to, X is 0, right? And then it increments it to 1. Is 1 greater than 100,000? No. So then it calls itself again, prints out hello world a second time. X becomes 2. Is 2 greater than 100,000? Nope. So it goes on and calls itself again. So global variables are shared among every function indication. Yes, it is 100,001. And this is what I hate about programming, is off by 1 errors, right? So you're not going to want to count this all the way up to 100,000. So what I would do is put in the number like 1 here, right? And say cout hello world. Okay, so we print it out once. Increment X from 0 to 1. Is 1 greater than 1? No. So then it calls it a second time. So we need to change this to greater than or equal to, or we can put the hello world below the if statement, one or the other, and then our code will work the way that we think it should work. But here's the real kicker, is that if we ever call f a second time, like we think f is a function that prints hello world 100,000 times, and maybe we fix it so it does print 100,000 times. What happens if main calls f a second time? How many times will the second time we call f print hello world? Yeah. So how many times will it print hello world the second time? So we got down here in main, we call f, it prints out hello world 100,000 times. We maybe change this to be greater than or equal to. Yeah, maybe we fix it like that. Okay. So if we call f a second time, how many times does it print hello world? 1. Yeah. So globals are annoying. Try to avoid them if you can. Yeah. There's also a pretty good chance that this code will segfault because the function's calling itself 100,000 times. Do you guys remember how the stack works? Because we're going to be talking recursion. Do you need a refresher on how the stack and the heap work? Yeah? Okay. Okay, so you can conceptually think of the memory on your computer as like this. So memory address 0 is down here, and the highest part of memory is 7F. It's hex. Doesn't matter. It's just some large number. It's up top. The area down here I call the minefield of doom. So the area around memory address 0. If you ever access it, if you ever read it, write it, it will crash your program. Because you're not supposed to ever touch the memory around 0, but the OS will usually mark it off as like minefield of doom. This is not a technical term, it's just what I call it. And if you ever read or write to that, that means you screwed up. You had a pointer somewhere, somebody set a pointer to 0, and then you like tried couting what was at that pointer. If you do this, it's a segfault. We have some int pointer or something, and the pointer is pointing to 0. All right. If you try outputting what is at that pointer, then it tries reading from the 0 page here, and it will crash your program. Guaranteed segfault. Okay. So segfault is a segmentation violation. Okay. So there are different segments of memory. And you got up top here a segment of memory called the stack. The stack grows downwards. And then above the minefield of doom, you have your code segment. And the code segment holds all of your assembly, essentially. in 0 and 1 form. So your program is actually held in a memory segment, and this is usually marked read-only. Back in the day, code segments used to be writable, so you could do really clever optimizations like rewriting your program as it ran. Like if you are running and then you realize that this whole chunk of code or the data that you're working on will never have these if statements be true, you just eliminate those if statements while your program is running, which is pretty amazing. But nowadays we don't do that. We don't do self-modifying code anymore. So typically the code segment is marked as read-only for security reasons, because otherwise you could overwrite the code, like somebody's web server, is running, and you overflow the stack and you write data into here, and you can change the program as it's running with root access, which would be bad. Okay. Above the code segment is the BSS. The BSS is where globals live. So we had a global called X, right? That was equal to 0. That's going to be in the BSS somewhere. And what was our other one? A limit. That's a constant. It's probably not going to exist at all. So constants don't exist, usually. Sometimes. They can be optimized away. They usually don't actually have a memory address. Okay, so above the BSS is the data segment. And the data segment grows upwards. And this is when you new things. So when you say new int array, 100,000 or something, that's going to create a chunk of 400,000 bytes on the data segment. And you've got something called the break pointer. The break pointer moves upwards when you need to grow the data segment. The stack has something called the stack pointer, and the stack pointer goes downwards. The stack is for normal variables. Normal variables go on the stack. So if you have a function, it has some variable in it, like int x or something. Oh, we already have an x. Int y equals 50. Y is going to be held on the stack. Y is going to be over here somewhere. And when we call f, what happens is the stack pointer moves down, and it moves down far enough to hold all of the variables that you need for that function. So it holds y and it sets that equal to 50, and the stack pointer moves down to here. And then when f calls f, the stack pointer moves down again, and it allocates enough memory again, because there's now 2 copies of y. There's the original y, the OG y, and now there's the new y. And then f calls itself again, and it allocates another y. And so what happens is the stack pointer starts going downwards like this. And there is a limit to how much stack you have in your program. And on our system, the stack is set by default to, I think it's not very large, but stack size is set to 8 megabytes. So all those variables you make, ints and floats and doubles, all those regular variables you don't know, just regular variables, all of those are allocated automatically for you on the stack. And how do they get deleted? Well, they get deleted when the stack goes back up. So when you return from a function, then the stack pointer moves back up where it was before. And then you return again, and the stack pointer moves back up again. And so every time you call a function, the stack pointer moves down. Every time you return from a function, the stack pointer goes back up. And it moves down far enough to give you, it allocates all of the memory all at once. And then you call the function again, it goes down again. And then when it returns, all those variables go away. Okay. And there's something called a frame pointer that is like, the frame pointer is kind of like the last stack pointer, so it knows where to return to. So it kind of marks the top of the frame. Okay, makes sense to you guys? So anything allocated on the stack, you don't need to worry about the memory allocation or deallocation. It just takes place automatically. It's really nice, it's convenient. Can't leak memory, Things on the data segment, when you new them, it will allocate a chunk of data down here on the data segment. And so on our system, the stack is technically 8 megabytes, although it crashes around 100 megabytes. It won't throw a seg fault until you've used up about 100 megs of stack space. Although the last time I tried it, it did crash at 8. Like you can't you can't rely on this. All right. So you can make it bigger if you want. If you want more stack space. 8 megs isn't very big. And the reason why it's small though is because if you have a runaway loop, if you have a runaway recursive function that calls itself, which calls itself, which calls itself, which calls itself, and never not calls itself, like our original version here, then the stack is intentionally limited and intentionally kept small so your program crashes quickly. Okay? Because what happens is that you've got a limit somewhere over here. And if the stack pointer ever crosses that limit, it stepped over the line, seg fault. Okay? You guys remember this now? So whenever you work with recursion, one of the things you have to ask yourself is, what is the maximum number of times I'll call myself? And then you have to sit there and say, all right, how much memory does it allocate per frame? Because there's a minimum of like having the return address and stuff like that. How much memory is allocated per frame? Okay, so how many times can I call myself? And you can kind of like eyeball it, right? Or if you don't want to eyeball it, you can just come up in here. I'll make it a random number so the optimizer can't eliminate it. Anyone want to take bets on how many times we will be able to call f before it seg faults? I mean, I set y equal to a random number. That way the compiler can't eliminate it. Because if you eliminate it, then it doesn't allocate memory, right? And there's a lot of tricks that compilers will use to stop you from seg faulting, which we're not gonna do here. 1,000 times. All right. So remember, our stack size is 8 megabytes. 3.14. Anyone else? Put your bets down now. Most accurate guess gets a point on their quizzes. Most accurate guess gets an extra credit point. Place your bets, ladies and gentlemen. Place your bets. 8 million times. Spinning a roulette wheel. 2048. Whoever's closest gets the extra credit point. 512. 1024. There's probably some advantage to going later, so you can bracket your teammates. 1. All right, it's going to print 1. So let me tell you what the counter thing here does. This is a static variable. How many people here have never seen this before? A static variable like this. Everyone's seen this before? Come on, you can admit it. How many people have never seen this thing in C++ before? We can all use a refresh. That's a very political way of putting it, Mr. Singh. So, what this means is static here. Static is one of those weird keywords that comes up in different contexts. Here it means counter is a global only accessible in this scope. So it's like I had written this. Except main would be able to mess with counter, right? Right? That's fine. But if you make it a static, then it's a global. It's going to be allocated in the BSS, the BS segment, but it is only accessible within F. And so what we can do here is keep track of how many times this function was called. Okay. So every time we call F, it's going to print out counter. It's going to print out 0 the first time through, followed by a colon, followed by some random number. And then after this outputs, counter is going to increment by 1. And so even it'll be preserved through all the different function calls because it's a global. It's not a stack allocated variable anymore. It's a BSS allocated variable. It's a global. Okay. And so this is actually a very common use for a static variable, which is to count how many times a function gets called. Like if you want to find out, like, hey, where am I spending my time? Like people will make counters like this, and just every time the function gets called, it just increments it by 1, and then it writes it to a log or something like that, you know. And then you can come back in and be like, oh, look, this function here is my hot loop. You know, right here we've got a function that is being called 1,000,000 times. This one's being called 100 times. Let's focus on the one. Let's focus on speeding up the one that runs 1,000,000 times. You know, and there's tools called profilers that do that for you. But okay. Any other bets? Guerrero, Vargas, Sarah has 1. Pata, I don't know if Pata's even here. All right, so let's spin the wheel. Spin the roulette wheel. Let's see what we got. Let's turn off the optimizer. Well, let's run for a while. Okay. Any questions about the memory map? Okay. Might be. If it doesn't move the stack pointer at all, like if it optimizes it away, then it could run forever. I turned off the optimizer though, so it shouldn't. Okay, so it's recursively calling itself a lot of times. And part of the reason for this is because we're not allocating any variables off the stack. All right. The only thing we need to keep track of is our return address. So when we return, which we don't do, we can go back. Still running. Okay. Do you guys all understand this? The data segment, BSS, you know where data goes. What about a vector? If you have a vector, if you make a vector of size 1,000,000, where does the vector get allocated? I think we have a winner. Segfault, core dumped. 3.2 million is the winner. Looks like Vargas. Everyone clap emoji for Vargas. Everyone work on their 4D homework just came to a halt. Yeah. It's their fault for being on the server while I'm lecturing. Close, Mr. Singh, close, but not quite. Okay. So, recursion. So when you recurse, the stack pointer moves down, and there is a max number of times that you can recurse. And so It depends on if you're making variables within the function. If you do so, like let's offer another point for extra credit. Let's make a integer array of size 256. So every time we call f, it's going to move the stack pointer down an additional kilobyte. Okay, additional k. It's going to move down. So how many times can we call the function now? Put your bets in, people. Put your bets in. Spin the roulette wheel again. It'll probably be a lower number than what we had before. Extra credit is on the line. What you got? Place your nuts. Place your bets now, people. Seeing going with 256,000. See, now you let them type first. See, now you put in 256,001. It's like the Price is Right approach, And see, now, Mr. Singh, you edit your thing. No, you can't edit it. Once your bets are in, your bets are in. Okay. All right. Anyone else? Pada, are you here at all? Cohen? Yeah, I got you. Pada is here at 200,000. All right. McCohen, you here? I think you're the last one. Get this ready to go. 259999. All right, here we go. Snap that. Oh, there we go. Cycle. So 95,515 is the winner. So looks like Vargas again. Two extra points for Vargas. 0 extra credit for everyone else. Thanks for playing, everyone. See, I just was private messaging Vargas the answer. No, okay. Well done, though. Well done, sir. So recursion is useful. So one thing I do want to get clear to you is that recursion can crash if it goes on for too long. So one question you have to ask yourself is my code going to crash if I use recursion versus a loop? Because recursion is just a different way of doing a loop. There's nothing, fancy about recursion. You just have you're using the stack of the system instead of a for loop in this case, right? So this could be done with a for loop, 100,000 times print hello world, all right? And unfortunately, when you use the stack as your counter somehow, if you run out of stack space, your program dies. It's unrecoverable. Running out of stack is one of the few bugs you really just can't come back from. And the reason for that is any code you would write to come back from a Stack Overflow, you'd have to call the function. In order to call the function, you need stack space for it, and you can't. So it's one of those situations where you just can't really do anything, and it just kills your program. At Microsoft, they don't allow writing code like this because all of Microsoft, at least when my friend was working there, all of Microsoft, not all of Microsoft, but all of Microsoft, for most intents and purposes, ran on a common framework called Zen or something like that. And so you'd basically, if you wanted to process Dijkstras for the country, it would run on it. If a person wanted to get the weather in Duluth, it would go to a web server, and then the web server would query this middleware with sort of an abstract machine layer that would sort of hide the details of the data centers away from the programmers. The programmers would just submit a request, hey, run Dijkstras, and then this middleware layer would execute the program on whatever data centers there are. And if any one of those 1,000 teams at Microsoft Stack Overflowed, the entire middleware layer went down. So it would crash Microsoft. Not your program, not the web server. It would crash Microsoft. And so my buddy, when he was working there, he was working on the Cortana team. I don't know if you guys have heard of Cortana. It's an AI from Halo that somehow became the search engine for Microsoft. And they actually kept their middleware layer separate so that if Microsoft went down, Cortana wouldn't go down also. They had their own thing. But basically, if you ever wanted to write a recursive function that would run on this middleware layer, you had to be damn certain and that you could prove to people, because they did code reviews, right? Like we kind of do. You had to prove to people that the maximum recursion limit would not be hit in any circumstance. So most of them would just they had a, like when you submit your code, a patch, one of the things they would do is see if you called yourself, if a function ever called itself. And sometimes it can be tricky, right? Like if you have F and F calls G and then G calls F, that's recursion also, right? And so it would actually do like a graph theory thing, like F calls G and G calls H and H calls F. And so there's cycle detection algorithms. Graph theory. Graph theory is everywhere, I'm telling you. And so their code analysis tool would actually generate a graph of which functions call which functions. And if there's any cycles within the code, like this, it would reject. Be like, nope, your code's recursive. Because it would take out Microsoft. Or potentially could take out Microsoft. And so you had to get like special approval to write a recursive algorithm. Would image processing have concepts of graph theory? Yeah, I mean, a lot of times you're doing image filters, you're grabbing data to the north, south, east, west, northeast, northwest, southeast, southwest, right? So, yeah, comes up everywhere. Okay, so that said, sometimes you can write a function that's very beautiful, right? So if you have a tree, if you have a binary search tree, again, this class requires 41. But the basic rule for a binary search tree is that everybody to your left is smaller than you, everybody to your right is bigger than you, okay? And so you can write DFS very cleanly and very beautifully by simply saying print everybody in the left subtree, then print my value, then print everybody in the right subtree. It's a DAG. It's a directed acyclic graph. What's wrong with this DFS code? I just gave you a clue. Talk about Microsoft. Actually, a couple. There's two very major. There are two very, very large glaring problems with this. There's only 3 lines of code, so hopefully you can find at least one of them. Checking for null pointer, very good. That's where we're in. Yeah, whenever you work with a pointer, first thing you need to do is check to see if it's null, right? So if we recurse off the left side of 1 here, this is null, right? And so we would do this null dereference here, and that will crash. So this code is guaranteed to crash, one way or the other. The other way it could crash is what? You guys see what I'm getting at here? This is a binary search tree. Not a very good one. It's not a balanced binary search tree. What could cause the crash? Come on, people. You're on Discord. You're on Discord for a reason. Drink your coffee. What's the crash? One crash is dereferencing a null pointer. Another crash is due to... No, this code will never go right. This code, when you call DFS, it calls DFS on its left node. And then when you get to DFS, you call DFS on that one's left node. When you call DFS, you call DFS. These two lines of code will never run, by the way. The way that we have it written right now. Nope. These two lines of code never run. This is an infinite loop here. Do you see that? DFS calls DFS, which calls DFS, which calls DFS, which calls DFS, which calls DFS. It never will print out anything. But that's not even the crashing bug. What's the crashing bug? One of them is null pointer dereference. What's the other crashing bug? There's a famous website named for this bug. It's called a stack. Google. No. Stack Google. Stack Overflow. Very good. Yeah, Stack Overflow is a website where they have answers for technical problems and people being snippy at each other. So, Stack Overflow, yeah. What's going to happen is if we have a big unbalanced tree like this, then it calls DFS to the left, DFS to the left, DFS to the left, DFS to the left. And eventually we'll run out of stack space. Right here. The stack pointer moves down every time you do a function call. And if it crosses over that dotted line, then it will segfault. It will stack overflow. Okay? So, stack Google. That's fine. Yeah, so this code has 2 lethal bugs in it in 3 lines. It's pretty bad. Let's clean it up a little bit. So let's add in a null check, right? There's a lot of different ways you can check for null. There's the better way of doing this is n is equal to null pointer. The better way of doing it. Or you can say n is equal to 0 if n is equal to 0, or if not n. These are all different options for doing this right here. If n equals null, return. So this is better. This is better. It still has a crashing bug in it. How can I crash? How can I feed a valid binary search tree to this algorithm that will cause it to crash? I've stopped the null dereference. What bug remains? Silence. There were 2 bugs before. I got rid of one of them. What's the other bug? Still not running the last 2 lines of code. It is actually now. Because if we DFS down to the left, and the left node is null, then it returns. And it will, when you return, you come back up into the previous function call and move on to the next line. So it will, in fact, print. This code is actually going to work for most everyday situations. It will still, it's not infinite either. If you pass it a valid binary search tree, where the null pointers are set properly, this code will work most of the time. It will not work some of the time, and that terrifies computer science people. If you were at Microsoft, would you allow this to run on your Zen middleware? Can you guarantee that this will not stack overflow? Could you stack overflow and take down Microsoft using this code? What do you think? All you have to do is say yes or no on Discord. I'm just going to sit here and wait. You cannot guarantee will stack overflow. Yeah. Why? What tree could you feed it that will cause it to stack overflow? You're testing this code. What tree are you going to test it with? Same tree that I had before, remember? A completely unbalanced tree that looks like this. 100, left child 99, left child 98, left child 97. If you make this completely unbalanced tree big enough, then it will stack overflow. You guys see that? You need to think about this. So, here's the secret to thinking about recursion. And this is our big learning point for today. There's two things you have to have in every recursive algorithm. You need to start looking at recursive algorithms in this mindset. Okay? Two things you need. You need to have a terminating base condition. With our first version of the code here, we did not have something that stopped the recursion from recursing infinitely. So we added it in. So that's this one here. You must have a, if, something is less than 0, return. You have to have some way out of the infinite loop, right? Our first function here had no, well, I guess it did have a way out, but this is the second problem. But this one, notice it just DFS calls DFS, which calls DFS, which calls DFS, which calls DFS, which calls DFS. There's no way out of the infinite loop here. This is an infinite loop. It will infinite loop, it will segfault, or run forever, depending on if the optimizer can play with it or something. So there's two things you need. One, there must be a way out. Two, you must always advance towards the finish line. So if you've got a football field here, you got the 50-yard line, you got an end zone. Think about it as the person must always run towards the end zone, and there must be an end zone. So the thing must stop when you get to the end zone. You don't want to be Forrest Gump. Forrest Gump would hit the end zone and just keep running, right? You must have an end zone that stops the player from crossing the finish line, and you must always move towards, no matter where you start, you must always move towards the finish line. And if you want to get technical, you could theoretically run away a little bit and then come back in, but you must guarantee that your code must always hit the finish line. Okay? These are the two things that you have to have in every recursive function. You must have a terminating condition, a terminating base condition, and you must have a recursive step that always moves you towards the finish line. Okay? So here, which one of those two things are we missing? Do we have a terminating step? Yes. Are we always moving towards the finish line? No. Why? Because x doesn't increase. You see that? So we had the first one, we had the finish line. We had something that will stop the recursion from infinitely recursing, but we did not move towards it. And so we fixed it by putting a plus plus in there, so that x will always move towards the finish line. Infinite loop, non-infinite loop. Infinite loop, non-infinite loop. And then the third thing you need to worry about is is it going to crash anyway? Because there's a stack limit, right? There's a limit to how many times you can call yourself, right? It's what you were taking bets on earlier. How many times can it call itself before it crashes? Every recursive function has a recursion limit, maximum depth of the stack. Okay, so also think about the depth limit. How many times can you call yourself before it crashes? Okay, so what do you think? Is this code going to end, or is it going to loop forever? What do you think? Got 12 minutes left in class. Let's do some lightning rounds here. Is this code going to run forever, i.e. segfault when it runs out of stack space, or does it terminate? Vargas is putting a bet down on infinite. Yes, if you pass in 2, it'll print out hello 2. Then it calls hello or 2 again, and it prints out hello 2. And then it calls hello or 2 again, and it prints out hello 2, and it does this infinitely. There is no terminating base condition. There's also no movement towards the base condition. It's supposed to print out hello 2, hello 1, and then terminate. It does not either have a goal, nor does it have the inductive step to move it towards the goal. How about now? How about now? Is this code correct now? Which one am I missing still? It'll crash. Yeah, it's an infinite loop, but an infinite loop in a recursive function will turn into a segfault, right? Whereas an infinite loop in a loop will just loop forever. There's a difference. Yeah. We're missing the terminating base condition. We've got the inductive step down. The inductive step will always move us towards the goal, which is 0. But we don't actually have the finish line. We don't have any way. There's no return from this, right? This is helloer will call helloer, which calls helloer, which calls helloer. This is an infinite loop still. Okay, so let's add this in. Is it correct now? We've got a base condition, and we've got a base condition. Is this code correct? Is this code correct? It needs to have an x minus minus, right? Or when you call helloer, you need to pass in x minus 1. Also, this is an off by 1 error. It's supposed to print, if you call helloer 2, it should print out hello 2, hello 1. This code will not print out hello 1. It's got an off by 1 error in there. If you pass in helloer 1, it just returns. Okay? So the base condition is wrong. We set the end zone 1 yard ahead of the actual end zone. We stopped too early. Okay? Yeah. And the inductive step is wrong. We've got a base condition. At least we got a base condition that will stop it, but it's wrong. It's 1 yard ahead of the finish line. And we're missing the inductive step. So when we say go, the football player just stands there with the football and never charges towards the finish line. And so it's an infinite loop. What about this one? So we fixed our base condition. Our base condition is now at 0. So when we hit 0, it terminates. X minus minus is going to print. So if we pass in 2, it's going to print hello 2, then decrement x to be 1 after the cout statement. So that's correct. If we did minus minus x, it would print out hello 1 for hello or 2. So this is x minus minus is correct here. So if we call hello or 1, it doesn't return. It prints out hello 1. X decrements to 0. We call hello or 0. X equals 0. It returns. Yes, very good. Negative numbers are not handled. And this is a mental blind spot that a lot of programmers have, which is they just don't consider that integers can be negative. Half of all integers are negative, right? And a lot of programmers just have a blind spot. Well, why would somebody pass in hello or -5? That doesn't make any sense. You're the one that said it's an int. If you said it's an int, You're saying it can be positive or negative, between positive 2 billion and negative 2 billion and change. You're the one that came up with that int thing there, buddy. If you wanted it to be an unsigned integer, make it an unsigned integer. You guys understand? So, if you want an unsigned integer, make it an unsigned integer. It's not gonna, it's not gonna hurt you in this case. Okay? So, if you say int, you have to get into that mental habit of like, okay, what if it's 10? What if it's 0? What if it's 1? What if it's negative 1? What if it's 100? What if it's negative 100? And so whenever you're writing code, like your brain just has to go to the extremes. All the edges. 0, a million, negative a million, 1, 10, right? And just you sort of mentally like have to run through your mental calculator if your code handles all those cases. One of the best things about discrete math is that it does sort of teach you to think that way. Okay. What about now? We've got a function, and if we ever hit 0, if we ever hit the end zone, we return. Otherwise, we flip a coin. If we get heads, we walk forwards. If we get tails, we walk backwards. Actually, we're rolling a 3-sided die. And if we get... Yeah, so basically we're going to either return +1, -1, or 0. If we get 0, we stay in place. If we get -1, we walk away from the end zone. If we get +1, head towards the end zone. So we have a 1 out of 3 chance of walking towards the base condition. We have a 1 out of 3 chance of walking away from the base condition. And we have a 1 out of 3 chance of standing in place. Will it end? Will this code terminate? It will terminate in one case, which is when you call random walk 0. It'll guaranteed end. Will this code end? And for this one, negative numbers and positive numbers actually don't matter, because you sit there and you're sort of vibrating in place, right? Randomly vibrating. It's Brownian in motion. And so if you have a negative number, it could vibrate on top of 0 and terminate. If you have a positive number, it could vibrate down to 0 and terminate. Or it might not. It's random. You don't know. There's no guarantee that it will terminate. And in fact, on average, it won't. On average, it stays put. Because it's a 50-50 chance of moving towards the end zone, 50-50 chance of moving away from the end zone, right? We'll just ignore staying still. And so, on average, it stays in place. Okay. So it might end, might not. Try running it. See how often it terminates. Okay. What about this one? Got the Fibonacci sequence here. So the Fibonacci sequence is a classic recursive problem, right? So it's a sequence where each element in the sequence is defined as the sum of the 2 previous terms in the sequence. So if we want to get the Fibonacci that's 10th in the series, we will call Fibonacci 10, and that will add up Fibonacci 9 and Fibonacci 8, sum them together, and that's the result for Fibonacci 10. Do we have a base condition, and are we always moving towards it? What do you think? Is there a base condition, and is our recursive step always going to move towards the base condition? We've got 4 minutes left. You got to say something. Yes, exactly, Mr. Vargas. Negative numbers are not handled here. I said you can pass in an int, but I'm not handling it. Very common bug. Very common bug in computer science, where a function takes an int, and if you pass in a negative number, infinite loop. Right? It'll run for a while, and then it'll cycle if you pass in a negative number. And this is something that I just really try to drive into the heads of my students, which is always vet your input. Don't trust, don't have your code have half the numbers cause your code to crash. I do not write code that crashes. That's like my own pet peeve. Like I've been criticized before for being too defensive, for having too many if statements to like make sure my code doesn't crash. They say it's not your responsibility to make sure your code doesn't crash. It's the other person's responsibility. To which my response is, you may be right, but I still don't like my code crashing. And so I will put if statements in there. I'll put asserts, static asserts, all sorts of things, so that if bad data comes in, it will notify you. Like, hey, you passed a negative number to Fibonacci. Okay. And sure, the code's slower, but I mean, my take on slowness is I write code that's slow and safe, and then if I need to make it faster, I can go in and pull the checks out afterwards if I have to. Or I can have the if-def release mode. Pull out all those sanity checks, pull out all the safety checks, pull out all the vetting. Sure, there you go. But most of the time, my CPU is fast enough. All right, what about now? What do you guys think? Wrong? What's wrong? Do we have a inductive step that always moves towards the finish line, the base condition? And do we have a base condition? Give me a case where it doesn't work, Carrie. Got enough off by one error. If it's 1, shouldn't it return n? No, because element 0 is 1 also. The Fibonacci sequence is defined as element 0 is 1, element 1 is 1. And then all other elements are defined as the sum of the 2 previous entries in the series. Some people do Fibonacci as saying element 0 is 0, element 1 is 1, and then it becomes so that they define it as 0, 1, 1. But the way I have it on the slide here is it starts as 1, 1, 2, 3, 5, 8, 13. So you're probably familiar with the different Fibonacci series then. See? Anyone see the problem with this code? Vargas? Sarah? What is the problem with this code? What's wrong with the code? Anyone see it? Technically, probably shouldn't return 1 for negative 100. Should probably, I don't know, die or something. But, that's not really a problem to me. If somebody asks me what a negative 5th Fibonacci number is, it's not really defined, so 1 is accurate because it's not defined. So what's the problem? What's the problem with the code? Let's try it out. Fibonacci of 1 is 1, Fibonacci of 2 is 2, Fibonacci of 3 is 3, Fibonacci of 4 is 5, Fibonacci of 5 is 8, Fibonacci of 6 is 13. Seems to be getting the right numbers, right? What's wrong with the code? Check 0. 0 is included in the less than or equal to. What's wrong with the code? Let me give you a hint. There's 2 things wrong with this code. Good. Guerrero is absolutely right. If you pass in a large Fibonacci number, you will segfault. Right? So there's no max here. If you pass in 4 million, as we've seen, it'll segfault. So this code doesn't, it's, maybe we can add in something. I don't know, we can do something like that or something, So we could add in overflow protection like that, right? CC assert that x is greater than or equal to 0 and x is less than or equal to 200. So how about now? So if we run it, assertion failed. Assertion failed. What's wrong with it? All I'm supposed to be doing here is 50 additions or so, right? The order of this algorithm should be n, right? If I want to compute the 50th Fibonacci number, I should be able to do this using 50 adds, give or take 1 or so, right? What the hell is going on here? When you'd be doing like 3 adds at once, however you want to put it, the order, it's roughly linear. It should be roughly linear proportionally, right? So whether or not you're doing 2 adds per number, either way, whether you're doing 50 adds or 100 adds, it should be done by now, right? What if I were to write this using just a for loop or something? For int I equals 0, I is less than x, I plus plus. Let's do a vector, I guess. Vector events, fib. If I is less than or equal to 1, fib dot push back 1. So this is the base condition. Otherwise, effectively the recursive step, fib dot push back fib dot the last element plus fib dot at I. Yeah, let's just do this. Fib dot at I minus 1 plus fib dot at I minus 2. Fib dot back is the last element in a vector. It's shorter than writing fib dot at. You know, size, fib dot size minus 1. Is that correct? Let's find out. Off by 1. Segfault. Yeah, it's wrong. Interesting speed delay there. We're overflowing. So what's wrong with it? What's wrong with the recursive implementation? What's going on here? We are overflowing, and we could switch in GMP, but that's actually not the issue I'm concerned about right now, although that is an issue. What's the problem? We use doubles. Well, it's not going to be accurate. What we need to do is do that. That's it for today. So I'll let you guys figure out what was wrong with the code here. Okay? Why is it running so long? We'll pick it up on Tuesday. All right. See you guys.